Hello again, and now we are on our second or third topic in vector spaces. This is now basis sets. So we have had a look at the definition of a vector space. We've had a look at linear dependencies and linear independencies, and now we have a look at basis sets. The very first thing is the dimension. Now, intuitively, you know that two-dimensional space is two-dimensional because, well, it's in a plane. Now, what do you mean by that? Well, two-dimensional space is two-dimensional mathematically because there are a maximum of two vectors which can be linearly independent in this space. So two-dimensional real space is written as R squared, and here we could have a maximum of two vectors which are linearly independent. For example, A and B are linearly independent vectors. We can't have more than two vectors being linearly independent in this space. If we did, it would be a three-dimensional space. So this is the maximum here. So the dimension then is defined as the maximum number of vectors. So the dimension of a vector space the dimension n of a vector space V is the maximum number of vectors that can be linearly independent. Okay, all right. Now we know from two-dimensional space that in addition to these vectors A and B being linearly independent, we could also have C and D being linearly independent. In fact, there are an infinite number of combinations of two vectors which are linearly independent. Any one of these combinations can be used as the basis. So this is where we come to our second definition, and this is the basis. All right, let me write this down in full. If V is an n-dimensional vector space, then any, and this is important here, any set of n linearly independent vectors and I will call this set by curly braces E bar I. Now what this means, this is a short form for the set E1, E2, dot 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 all the way to En. All right, I'm going to be using that. So any set of these, any such set forms a basis of the space V. I have not mentioned anything about an orthonormal basis or a normalized basis. We haven't even discussed these concepts as yet, although you have an idea of what they are. All I've said is here is that if these are n linearly independent vectors in this space, then these vectors can form a basis for the space. All right, that's it. Now, if these are n linearly independent vectors, then the set consisting of another, so let me put it another way, then it follows that if we have another vector x belonging to the space, the set of vectors x, comma, and then all those other vectors I goes from 1 to n, this set must be linearly dependent. Now why? This is the point in time when if I was teaching in real life, I would be asking one of you or someone in the class, why should this be linearly dependent? So think about it. This set here consists of n vectors, and this is one more vector. So the total number of vectors in the set is n plus 1. Now we know that this space is of dimension n, and we just said that the definition of the dimension is that n is the maximum number of vectors that can be linearly independent. Now n plus 1 is more than n, therefore this set has to be linearly dependent. Okay? Now if it is, then so therefore I'm going to put this in red. We can write I goes from 1 to n, alpha I e bar I plus some beta x is equal to the 0 vector. That's the definition of linear dependency, right? I mean, now I'm going to assert, and then we're going to show it, that beta must be non-zero. Why? Now each time I put a y in my notes, I'd like you to think about it. So at this point you might even want to pause the video and say, ask yourself, why should beta be non-zero? So one way of looking at it is say, suppose beta is 0, in which case we would have the sum I going from 1 to n of alpha I ei plus 0 is equal to 0. And what we're then saying is that the sum of this linear combination of these basis vectors ei is equal to the 0 vector. But that's not possible unless all the coefficients alpha I are 0, because the basis vectors are defined to be a set of linearly independent vectors. But if the coefficients alpha I are 0, that means what I'm saying is that I've got all these coefficients 0, and therefore I get a 0 vector. But if the set is linearly dependent, then at least one of these coefficients must be non-zero by the definition. And if you haven't understood this, you have to go back to the previous recording on linear dependency. So the only way we can have this thing equal to the 0 vector and at least one of these coefficients non-zero is to have beta itself non-zero and possibly one of the other alphas also non-zero. I'd like you to think about this and really understand this. If you're not sure why beta must be non-zero, then bring it up in the tutorial sessions. All right, so if beta is non-zero, then what we can do is to write the vector x as minus 1 over beta, because we can now divide by beta. Beta is non-zero. Sum I goes from 1 to n alpha I ei, which is equal to the sum I goes from 1 to n alpha I minus alpha I over beta ei, and I'm going to just call this coefficient as xi. Effectively what we've done is to write the vector x in terms of the basis set with coefficients xi, and in short we would write the vector x as the column vector x1, x2 all the way to xn. That's what's meant by a column vector. What we are saying is that x1 is the coefficient of the vector e1, x2 is the coefficient of the vector e2 all the way to xn being the coefficient of the vector en in this expansion. Okay, we're nearly done. There's one more thing I'd like to motivate here. This expansion is unique. So given a basis, this is another way of writing I goes from 1 to n. Given this basis, the expansion, the set of xi are unique. Now this might seem trivial. Therefore, what this means is that we can write the vector x in only one way, as the sum. There's only one way of writing this, and therefore what it means then is if we had another way, if somebody came and said, look, I can write the vector x as I goes from 1 to n of some yi's ei, then we must have xi equal to yi. So can we show this? Alright, so let me repeat then. This expansion set is unique given a basis, which means that if x is written as the sum of xi times ei and also the sum of yi times ei, then we must have, so we have to show this now, that xi is equal to yi for all I in the set 1 to n. How do we show this? Well, let's put another page here. To show this, all we need to do is to say, let these two exist. Now we know that x is equal to x. Therefore, the sum I goes from 1 to n, xi ei is equal to the sum I goes from 1 to n, yi ei. Therefore, we can bring these two sums to one side and subtract one from the other. Xi minus yi ei is equal to 0. Is this right? No, it's the 0 vector. Okay. And then you look at this and say, one second, this is saying that these are my basis vectors. I know that the set of vectors ei are a set of linearly independent vectors. So the only way that a linear combination of these basis vectors can be equal to the 0 vector is if these coefficients are all 0 for all I. Therefore, xi is equal to yi for all I. And that's it. That means that these expansion coefficients are indeed unique. All right, so that's our definition of a basis. Just a reminder, the basis of an n-dimensional vector space is any set of n linearly independent vectors ei. Any set can be used as a basis for this space. Which one you use is up to you, but any one of them can be used. Right. I've also said that the expansion coefficients of any vector x in this space, the expansion coefficients, the xi's, are unique once you've defined a basis set. However, if I change my basis set, then the xi's will change. This is an important concept again. Are multiple basis sets possible for any given space? Of course. There are generally an infinite number of these. In two-dimensional space, any pair of linearly independent vectors can be used as a basis for that space. And although your vectors are immutable, the expansion coefficients of the vectors depend on which choice of basis sets you have. Alright, so I will end there, and the next topic is going to be the inner product. Let's stop this video.